that the spaceship wasn't moving even though it looked like it was, and it was actually the background the whole time. That's because your perspective was different than my perspective. Hi, I'm Gus Serrano, and today my friends and I are going to teach you about frame of reference.
Frame of reference video.
The way you see your world is called your perspective. But sometimes your perspective isn't always where it needs to be. That's why you can't always believe your eyes.
Hey,
Hey,
can I have some of that?
sure.
Thanks.
Sure.
Frame of reference video.
Another example is, it doesn't actually look like I'm driving when I really am.
Okay, so in the video you just saw, there were times when it looked like something was moving but it really wasn't, and times when something looked like it wasn't moving but it really was. Okay, so that has to do with the frame of reference, but it's not always something's moving and it's not, or something like that. It could be that from my frame of reference something looks like it's moving 20 meters per second, but from another person's frame of reference it looks like it's only moving 10 meters per second. Sometimes you might think of this more commonly used in everyday language as like your point of view. And we'll get into how that works on the next slide when we do a problem. Okay? So frame of reference, it's kind of like the point of view. The frame of reference defines what's not moving. Most often for the problems we say the Earth is our frame of reference. So we're sitting in the classroom, we're on Earth. Earth is moving. It's moving around the sun and it is spinning around on its axis. So we're moving, even though we say that Earth is our frame of reference. So when we're here in class, we're just sitting there, we say you're not moving. Okay? That is a little bit about frame of reference, point of view. So how does that affect our problems? A passenger at the rear of a train traveling at 15 meters per second relative to Earth throws a baseball at the speed of 18 meters per second in the direction opposite the motion of the train. What is the velocity of the baseball relative to Earth as it leaves the thrower's hand? Alright, so let's go ahead and look at this. We've got two vectors, okay? We've got one vector representing the train, and that's going to the right in this picture, and the train is traveling at 15 meters per second relative to the Earth. The baseball is traveling with a speed of 18 meters per second in the opposite direction that the train is moving. So we want to figure out, if you are a bystander standing over here, what does it look like to you? How fast does it appear the ball is moving? Well, the train's moving to the right and the baseball is moving to the left. So these are kind of working against each other, okay? So when we go to figure out how fast the baseball moves in your perspective, we've got two vectors here. We're going to add them together, but one's going to the right, the other one's going to the left, so we're really going to be subtracting. So I'm going to take 18 minus 15, and I get 3 meters per second. And to determine which way, which direction the baseball appears to be moving, we simply look at which vector had a larger magnitude, which was the 18. So it's going to be moving to the left. Okay? So to a person standing on the ground, the baseball appears to be moving at 3 meters per second to the left. All right, that's a fairly easy one. The next one steps it up a little bit. This time we have a ferry crossing a river. If the ferry is headed due north, so the ferry's here, and they are going due north, they're just moving straight ahead, okay, with a speed of 3.5 meters per second relative to the water. And the river's velocity is 4 meters per second to the east. So here's your river, and your river is flowing that way, okay? You're going north, but the river's flowing that way, so it's going to push you over, okay? So it says, what will the boat's velocity be relative to Earth? So to figure this out, we're going to use some vector addition again. So I've got my 3 meters per second north, and I'm going to add the 4 meters per second east to that. Remember, line these up tip to tail. So the first thing I want to do is figure out how fast it's going. Well, I've created a right triangle here, so to find the missing side, okay, I'm simply going to use Pythagorean theorem. So 3.5 squared plus 4 squared is equal to c squared. Go ahead, do a little math. We get 12 and 25 hundredths plus 16 equals c squared. And we get c squared is 28 and 25 hundredths. Take the square root. And we get 5 and 32 hundredths meters per second. It's only part of my answer, though. I still need the direction. Well, good thing we just did some trig, okay? We are going to use some trigonometry again. Let's find this angle right here. I'm going to label it as theta. So I need to find that angle. Well, I look at the angle and I say 4 is opposite, 3.5 is adjacent. So I've got my trig functions with the memory aids, SO, CA, and TOA. I've got the opposite and the adjacent, so I'll use tangent. So the tangent of the angle is equal to the opposite, which is 4, over the adjacent, 3.5. I need to get rid of the tangent, which means I need to do the inverse. So I will take the inverse tangent of each side. Over here they cancel out, and I'm left with theta equals the inverse tangent of 4 over 3.5, which is 48.8 degrees. To write this out, I'm going to go ahead and write my answer all together. I'm going to say the velocity is equal to 5.32 meters per second. And then I'm going to go ahead and draw my angle. Well, my angle in the picture is this angle. So I'm going to draw a dotted line vertically going down, and then a solid line representing my vector going over, and this was the angle that I found. Okay, and then I'll write my angle. So 48.8 degrees.